Hi everyone. Today we are going to continue our discussion about the quicksort, and that's the hardest and the most mathematical part. Probably not just for the quicksort, but for the entire course. Okay, well, I'm not enjoying teaching to this content, but as a master level algorithm course, you can see that. But before we talk about the quicksort, here are some very quick updates about this course. Well, I have to update the hyperlink of my office hours. So start from today, and my office hour hyperlink will be this one. And the reason is Zoom recently updated their requirement about the security of the individual rooms, and I cannot use a room without any security, without password, without waiting room, and without any required login credentials. So it doesn't work this way. So I have to add a password to my room, and then from now on, if you want to come to my office hour, and make sure you are using this hyperlink. Okay, and then let's move on and talk about midterm one. And remember, the midterm one will be this week on Thursday. Okay, well, for this midterm, this will be a closed internet exam, and you are supposed to work on all the questions by yourself. And during this test, there are some of the allowed reference you can do. Like you can use your own notes, and you can use my lecture notes or the lecture videos. And you may say, hey, you just say close internet, and so how can I watch the videos? Okay, so if you are watching my lecture videos on YouTube, that's fine. That's the only possible use of the internet when you are working on this midterm. Okay, and then your own homework solution. So those are the references you are allowed to use during the test. Okay, and then other than that, you cannot send emails. You cannot have other people answer your question. You cannot help each other or sit together and discuss anything, or use checks or Coursera or this kind of online platforms. And if I see any violation, and we are gonna have a really serious talk, and this kind of cases may go really ugly. So please, everyone, don't try anything funny. You are gonna give yourself big trouble. Okay, well, let me provide a study guide on what are the concepts you are supposed to know. Well, the very first thing, well, remember at the very beginning of this course, we spent time to review the basic Python programming and plus the basic data structure, and they are not tested. But I'm not creating questions to test those things. However, there will be questions. Say I ask you to write pseudocode, or I ask you to write real Python code, or I may expect you to know how does the array work in Python. And if you don't know that, then you're gonna have trouble. And the next topic is induction. And remember, there are three major steps for the induction. What's the basis? Where do you start from? And then number two, what is your inductive hypothesis? And number three, starting from the inductive hypothesis, and how do we prove that if n is true, and then the n plus 1 is also true? Okay, so induction, that's an important topic. And by the way, I have a one extra video talking about another example of induction. Make sure you have watched that one. Okay, and the next topic is asymptotic notation, and we are talking about the big zeta. And before the big zeta, we have the big O and big omega. And then how do we prove the asymptotic notations of a given algorithm? And remember, we are counting how many primitive steps we are going to execute before we can have the result if the input size is n. Okay, so the total cost of running this algorithm using n as the input size will be the tn. And then based on a polynomial version of the tn, and then we can prove the big O, big omega, and then putting them together, we have the big zeta. And the next topic, some common asymptotic performances. And for example, what is the fastest and what is the lowest possible? That should be constant. A constant algorithm means, well, no matter what is the size of the input, and then the running time is always constant, and then there's no change. And what's the next best one? The next best one should be O log n. O log n is the next best. And then what's the next? The next is probably the linear, which is On. And if we move on, we have n log n. And if we go higher, we have n squared, etc. Okay, so when I gave you a bunch of the asymptotic performances, and I ask you to sort them from high to low or low to high, and then you should have that in your mind. Okay, well, and there are some of the algorithms we have already discussed in this class, either in homework or as a algorithm analysis or other algorithm we have discussed about. And for example, for the sorting, we have insertion sort, we have bubble sort, and we have the merge sort. And then we also talk about the search algorithms. We have the sequential search, and I probably you still remember the analogy I gave you. So if I walk into a classroom and then I'm looking for Bob, and then I can ask student A, are you Bob? And then I ask student B, are you Bob? So I just visit all the students one by one, and then that is a sequential search. And for the binary search, well, I'm gonna close my eyes, walk into the middle of the classroom, and then I'm gonna say, Bob, which side are you in? So if I hear Bob replies me on my right side, and then I know for the left side of the class Bob is not there, and then I go to the right side, and in the middle again I close my eyes and say, hey Bob, which side are you in? And then I listen where does Bob reply. So I always try to cut my search space by 1/2, and that is the binary search. Okay, and then for those algorithms we have already discussed, and then what are their asymptotic performances? And for some of the algorithms, then you want to distinguish their best case, their worst case. And for some of them, the best and the worst case, they're not the same. And for example, if we talk about quicksort, and then what's the best case of the quicksort? What's the worst case of the of quicksort? And then for best case and worst case of the quicksort, what are the time complexity, right? And then eventually, how do we prove them? Okay, and the next topic is recursion, and recursion is a important part because based on recursion, and then we have the master theorem. And if we don't have recursion, and then our life of analyzing algorithms will be much easier. But unfortunately, recursion is a very important family of algorithms. Okay, so how do you design the recursion algorithms? And there are two mindsets. And number one, we have the divide and conquer, right? And for example, merge sort. And number two, we if another well, the second strategy, I call that getting one step closer. And for those type of algorithms, you should be able to analyze, and you should be able to write the pseudocode too. Okay, and when you have a recursive algorithm, and then you should be able to come up with the recursive version of the Tn by reading and analyzing the code. And after we have the recursive version of the Tn, the next topic will be how do we solve the recursive Tn. And our goal is we start from a recursive version of the Tn, and we want to have the Tn as a polynomial of n. And after we have the polynomial version of the Tn, and then we can figure out the upper bound, we can figure out the lower bound, and eventually we have the big zeta. That is our goal. So, well, to solve the recursion, we have three different solutions. We have the substitution. Well, this is my favorite one. Remember, you want to divide your working zone into half. On the right side, we figure out the substitutions, and then we plug in the substitutions to the left side. And well, this is my favorite one because that's the easy one to do, the best one for the beginners. But you have to do a lot of writing. That's the part I don't like too much. And we have the iteration one, and if the recursion is not so hard, and then you get handy with solving recursions. The iteration one is a little bit easier, and you write not so much compared with the substitution. And eventually we have the master theorem. And the cool thing about the master theorem is we start from a recursive definition of the Tn, and then we analyze what is A, what is B, and what is Fn, and then using those information we figure out which case it is, and then we can jump after we figure out what case of the master theorem, and then we can jump directly to the big cited. So for the for the master theorem, you can save a lot of the writing. So master theorem is cool, but remember, master theorem cannot solve all the recursions. For some of them, and eventually if you find that you are not able to solve that with master theorem, and then you have to go back, you have to do either substitution or iteration. Okay, and then the heap. For the heap, this is a data structure, and based on this data structure, and eventually we introduce a sorting algorithm called heap sort. So, starting from the definition of the heap, and you need to know what is the heap, and then how it can be represented using the tree structure and using a 1D array as well. And what are the heap properties? And then there are 3 different functions we talk about. Number 1, what is heapify? For the heapify, we want to fix only one node, and we want to put this node down, and then we want, if the new location is still not the right one, we may have to pull it down again. So what does the heapify do? And it fixes one node. And what's the time complexity? The time complexity should be O log n. Okay, and how about build heap? And for the build heap, what do we do? What do we start? And then what do we finish? And then in this process, what is the time complexity? And then how about heap sort? And for the heap sort, and what do we start? And then what's the process? And can you work a heap sort out using on a piece of paper, given a list of the random numbers? Okay, and then using the heap, and we have a priority queue, and priority queue can be considered as a data structure implemented by the heap. And remember, in this class we talk about an example assuming that we are a very poor institution, and there's only one printer shared by a lot of people, and then all the people may send in the printing task to that printer at the same time. So this printer has to maintain a priority queue, and for that priority queue, and the highest the printing task with the highest priority will get processed first. Okay, well, if you forgot about that, and then you can go back, and I do remember I have done one example using that priority queue. Okay, and the next part, which is the topic we are going to finish today, the quicksort. So for the quicksort, and remember in our this book is so heavy. In this book, we do have a one implementation, but I decided that's not the version I want to go. So I provided you a more widely used version of the quicksort. So in this exam, feel free to use that version as well. And then, for the quicksort, the very important part is actually the partition. So what does the partition do? We separate the list of the value into 2 parts. So pivot in the middle, and then the values equal or smaller than the pivot, or the values greater or equal to the pivot. So we separate into 2 parts, and that's the partition, right? And then for the partition, what's the time complexity, and what are some of the better strategies in picking the pivot values? And remember, when we pick the pivot using the algorithm I give you, and then I always pick the first value as a pivot. And there are some smarter ways to pick the pivot values as well. And then after you understand the partition algorithm, and then we move on, and we can analyze the quicksort. So what does the quicksort do, and what's the worst case, what's the average case, what's the best case, and how do we prove the complexities of the worst case and the best case? Okay, so those are topics you are expected to see in the exam. So as a professor, I don't want to surprise my students in my exam. So I want to be crystal clear on what you are expect to know. And and the next thing, I'm going to show you a few of the sample questions. I'm going to show you. I'm going to talk about why I designed this question and then how this question can be answered. Okay, so let's see the first one. The first, assume that we have a quicksort algorithm provided in day 9 lecture, and then instead of using the first value as a pivot, now I want to plug in a new algorithm to select a pivot. And for the new algorithm to select the pivot, and it is a login. Okay, so instead of simply grabbing the first value as a pivot, now we have a small algorithm to select a pivot. And for that pivot, and there is a slightly higher cost, because if you just grab the first value to be the pivot, and then what's the cost? The cost is 1. That's constant. But for this selecting pivot algorithm, there's a slightly higher cost, which is log n. Okay, and my requirement is I want you to analyze the new version of the quicksort, and assuming that it does 90% to 10% split constantly. Okay, so that's not the best case, but it's not super bad either. So we always have 90% on one side and then 10% on the other side. And then I want to I ask you to prove the big O, and you have to explain the reasoning. Okay, so why am I asking this question? This is an algorithm tests your understanding of the quicksort, and plus it tests your understanding about the asymptotic performances. That is a quick question I created today, actually. Okay, so how do we answer that? So the number one question is, you gotta know what function does this algorithm change. I'm talking about the log n pivot selection selection part. So what function does this change? And the answer should be partition. You gotta know that. And if you visit the partition algorithm, I believe it should be in the first 3 lines. You grab the first value as a pivot. Now that line has to be changed. You want to call another algorithm to grab the pivot, right? So that's a partition. And the next question is, what's the new cost of the partition function? So, to answer this question, you have to know what is the time complexity of the old version of the partition. What is that? That is big O, right? And now if we want to add a log n to that, so we have a big O n. And then in this process, we also add a log n. What does this mean? N versus log n. Which one grows faster, or which one is more significant? That's the ON, right? So in the ON algorithm, when we add another log n, what does that mean? This means it doesn't change the time complexity at all, because anyhow it is already a ON algorithm. This means even though we have changed the partition algorithm, but the cost of the partition is still ON. Okay, the next part. After we know this information, how does that change the cost of the quicksort? And then remember, we have this kind of Tn, because we always have 90% on one side and 10% on the other side. And remember, I have drawn this kind of the tree structure that we are splitting. And then we have the 10% on one side and the 90% on one side. And then for this 10%, we will split that into 1% and 9%. And for the 90%, it will be split to 9% versus 81%. Remember, I have drawn this on my on my whiteboard, virtual whiteboard, I should say. So eventually, you will know that even for this part, it is still a ON. So this tree structure, and the height will be log, and the base number will be 10 divided by 9n. So this will still be a ON log. ON log n in this case, with the base number of the log as 10 divided by 9. So the short answer is it doesn't really change anything, because this log n, the cost of picking a better pivot, it will be absorbed by the ON algorithm of doing the partition. Okay, so this is a cool question. It tests really a lot of things. It tests if you understand the partition, if you understand the quicksort, and then if how to compare the O n versus the O log n, and then the analysis of the 90% versus 10% of the quicksort. So even this is just a small question, and probably I'm going to put 10 points to this question. It covers a lot of the aspects. Nothing super hard, but putting everything together, and this question can be a tricky question in the exam. Okay, in the exam, probably this question is a little bit harder, so I decide to show this question to you instead of give this question to you guys in the midterm. Okay, the second one. Solve the recursion below with the master theorem. Assuming that the base case is when n is 1, the cost will be 1. Okay, and for this kind of questions, I can give you any wild, crazy Tn's. I'm just giving you a few as examples. So Tn equals 3 Tn divided by 9 and plus n. And if I want to reverse the 9 and the 3, and then I have a different Tn, and then if you want to analyze them, and those two are quite different. Okay, let me just show you how to do one of them. Okay, I'm picking the first one. So Tn equals 3 Tn divided by 9, and then plus n. And remember, for this question, I'm requiring you to use the master theorem. So you don't have to really remember the master theorem, because you have that on your textbook or the course notes, so you don't have to remember them. But you do have to understand how to solve the recursions using the master theorem. And to solve the master theorem, the first step is you want to ask what are the b and the fn. In this case, it's quite simple. A is 3, b is 9, and then fn is n. Okay, so this is the first step. And what's the next step? Which one is faster, fn or n powers log ba? That is a very important question to answer when you're doing the master theorem. So what is fn? Fn is n, right? So fn is a linear algorithm. And then n powers log ba. What is that? Okay, log ba. b is 9, and then a is 3. So a log 9 3. What is that? If you don't know that, but you should know log 3 8 should be 2, right? So log 9 3 should be n 0.5, because if you have the 9 and then you do a square root and then you get 3, right? So this is log b n power log ba will be n powers 0.5, or the square root of n. Okay, and comparing the n versus n power 0.5, which one is higher? And you should know, okay, n is higher. And to be very accurate, following the case 1, 2, 3 of the master theorem, what we can say is, if you have the log ba and then we add a small positive value of the epsilon, and we can pick the epsilon as a 0.1, for example, and then we have n power 0.5 and plus 0.1, which is n power 0.6. But remember, this fn is n, so fn is still a faster one, and then n power 0.6 is the lower bound of fn. Okay, so this is case 3. So for case 3, that is actually a trickier case, because once you say it is case 3, you also have to do one more step of the proof. That is, you have using the given a and given b and the given fn, you have to prove that there exists a constant c, so that a f n divided by b is smaller than c multiplied by fn. So let's plug in the a, b, and fn. So what are we proving? So a is 3, and then fn is n itself, and divided by b, so divided by 9, and that is n multiplied by 1 divided by 3, or 1/3, right? So if we want to put it like this, so smaller than a constant multiplied by Fn, and what can this constant be? So 1/3 is smaller than 1/2. So n multiplied by 1/3 is smaller than n multiplied by 1/2. What does this mean? This means A multiplied by Fn divided by B is smaller than C multiplied by Fn. It holds when C is a 1/2. So after we have proven this part, we can finally say this is a scenario that we can apply the case 3. So, well, what's the case 3? Case 3 is the zeta Fn, so that is a zeta n. So, well, this is the cool thing about the master theorem, because you start from the recursive version of the Tn, and then after you figure out what case can apply, and then you jump directly to the big zeta. Okay, so for this question, when I design that, and I see a lot of the possibilities, and I can just plug in different values of the a and the b, and then different function of the Fn, and I can give you a wild collection of the Tn's, and I can ask you to solve them. And among them, in the case 3 is the hardest. And I have already shown you an example of the case 3. And if it is not case 3, and then you don't have to worry about this part. Okay, so that's a sample question 2. And let's move on to sample question 3. Well, that's the induction. That's a part I love. But for some of you guys, you really struggle a lot. So in this sample question, I'm going to show you another question about the induction. And by the way, I also created this question by myself today. Okay, so the question is, use the induction to prove that when n is greater or equal to 4, and then n log 2n is greater than n plus log 2n. Okay, and for the induction, and remember, there are always 3 steps or 3 major steps. And the number 1 is the base case. For the base case, well, I have already told you n is greater or excuse me, bless myself. Okay, so I have already told you that you want to start from the 4. So at least we want to prove that for the start point, which is n equals 4, this statement is true. So when n is 4, and then n log 2n will be 4 log 2 4, you will get 8. And then n plus log 2n, you will get a 6. So 8 is greater than 6, that is true. Okay, so that's a base case. We have already plugged in the number and proved that the base case is true. And then for the inductive hypothesis, you don't have to prove anything in the second step. You simply want to say that very clearly. That is the inductive hypothesis. We assume that for an given n value greater or equal to 4, the statement n log 2n is greater than n plus log 2n holds. Okay, we just assume it holds, and then the step 3, which is the harder one, which is the hardest one, we want to prove that for the n plus 1 it also holds. And this means for this equation, and then we want to substitute all the n's with n plus 1's, and it still holds. Okay, so on this page I'm showing you my thinking process. Okay, this is not what I'm gonna write down on my exam paper, but this is the thinking process of how do I prove this part. Our goal is we want to prove that, and then my thinking process is to prove this, and then how we can make this proof a little bit easier for me. So since we want to prove this part, and then I want to multiply the log 2 n plus 1 into both this n and then this plus 1. So I'm breaking this part, the left part, into 2 parts. So we have n log 2 n plus 1 and plus log 2 n plus 1. And for the right part, I'm not changing anything at all. And then you will notice that for this part, for the left part, we have log 2 n plus 1, and for the right part, we have log 2 n plus 1. So those 2 parts can cancel each other. So we only have to prove that n log 2 n plus 1 is greater than n plus 1. So we are getting a little bit easier, hopefully. Okay, and then I want to move this n to the left side. So this will be n log 2 n plus 1 minus n is greater than 1. And then I want to extract this n from the left side. So n multiplied by, and then log 2 n minus n plus 1, and then minus 1 outside of the log is greater than 1. Okay, so for this part I did, and after this part I did a small trick. I dropped the n. Why? Because I know n is greater than 1. And if I can prove that for whatever is in the square bracket, it is also greater than 1. And guess what? We have two parts. N is greater than 1. And whatever in the square bracket is also greater than 1. If we multiply those two together, we are guaranteed to have a value greater than 1. So I just drop the n, and then my goal will be I want to prove that whatever in the square bracket is greater than 1. And then, well, there's no need for the square bracket anymore. And then I want to move this negative 1 to the right side. So I want to prove that log 2 n plus 1 is greater than 2. So if the log 2 n plus 1 is greater than 2, this means the value of the n plus 1 is going to be greater than 4. And this means if we want to drop 1 on both sides, and then if we have to prove that n is greater than 3. Guess what? N is indeed greater than 3. Why? Because we are starting at n is 4, right? So for all the n values we want to touch in this question, they will be greater than 3, guaranteed. Okay, so we are trying, well, in this scratching part, what I have done is to prove this part, I want to prove this part, and to prove this part, I want to move down and prove the next part. And eventually, I want to reduce this problem size into something really, really small and basic, that is n greater than 2. But remember, for this is my scratching process. This belongs to my scratch paper. It doesn't belong to my exam paper because I'm doing reverse engineering. So how do I do the formal proof? For the formal proof, remember we are starting from the known, the most obvious part, which is n is greater than 3. And for the formal proof, where do we end? We end here using this line. This is exactly what we want to prove. Okay, so let me show you how I did that. N is greater than 3. Okay, obvious. We know that. And then n plus 1 greater than 4. Of course, we are adding 1. And then log n plus 1 is greater than 2 because n plus 1 is a value greater than 4. So makes sense. Okay, and then if you want to minus 1, and then whatever in the square bracket will be greater than 1, well, that's fine. And then if we multiply by n on the left side, that's also okay because whatever in the square bracket is greater than 1, and then we multiply another n that's greater than 1, so that's still good. And then we for this n, we want to move that inside of the square bracket, so we have the n log 2 n plus 1, and then minus n is greater than 1. Okay, and then for this minus 1, I want to move that to the right side. So I have n log 2 n plus 1 is greater than n plus 1. And after that, I want to add a log 2 n plus 1 on both sides. So we have the log 2 n plus 1 here. We have the log 2 n plus 1 here. And have we finished? No, one more step. For the left part, we want to extract the log 2 n plus 1 so that we have n plus 1 log 2 n plus 1 is greater than n plus 1, and then plus log 2 n plus 1. And then that's the end. Why? Because this is exactly what we want to prove. Because we know that for n, it holds. And now we are able to prove that for n plus 1. It also holds. Okay, so this is my formal proof of this induction question. Okay, and this is not an easy one. And for the exam paper, I'm gonna give you a slightly easier version of the induction. And if you're new to the induction and this is not a easy question for you. But even though you are not able to do the full formal proof, and remember how do you set up the induction. Number one, you want to prove that the base case or the basis is true. Number two, you want to put down very clearly what is your inductive hypothesis. And number three, you want to do a proof that if n holds, and then the n plus 1 also holds. And for the formal proof part, and usually I will do a reverse engineering on my scratch paper, and then after I have done that, and then I just flip everything, and then I will have a induction like this, and this is a formal proof. Okay, so those are three questions I want to show you, and hopefully this video can help you prepare for the midterm. Okay, good luck.